There's a distance from certain objects in space where the magnetic field becomes strong enough to rearrange the electrons in your atoms. Not push them around gently, literally yank them out of their orbitals, tearing apart every molecule in your body at once. Your cells wouldn't die, they would cease to exist as chemistry. And the disturbing part? From that same distance, you wouldn't see the object glowing. It would look like empty space. What kind of thing generates magnetic fields powerful enough to unmake matter from 1,000 kilometers away? The answer emerged from one of the strangest signals ever recorded. In 1979, satellites designed to watch for secret nuclear tests picked up something that looked nothing like a bomb, a burst of gamma rays arriving not from Earth but from deep space, delivered more energy in 0.2 of a second than anything astronomers had seen from such a source. For years, no explanation fit. The answer, when it came, involved magnetic fields at intensities that barely made physical sense. When massive stars collapse and form neutron stars, they sometimes trap the dying star's magnetic field and compress it violently. Imagine cramming the sun's entire magnetic field into a ball 15 kilometers across, roughly the size of a city. The field strength doesn't merely increase, it multiplies by factors of trillions. A typical neutron star carries a magnetic field about 1 trillion times stronger than Earth's. Write that out, 1 followed by 15 zeros. At that intensity, physics enters territory where normal intuition shatters completely. What would happen to a human body approaching a magnetar? The answer depends entirely on distance, and each distance kills in a completely different way. From relatively far, say a few thousand kilometers, where the field seems almost weak by magnetar standards, the trouble begins subtly. Magnetic field gradients at that range mean one side of your body experiences measurably different magnetic force than the other. Water is weakly diamagnetic. Magnetic fields push against it. Your blood, your organs, your brain, all are mostly water. The push isn't uniform. You'd feel a strange internal tugging, tissues being gently displaced where they shouldn't be. Prolonged exposure would cause internal bleeding, organ damage, slow death from forces inside you that can't be stopped by any wall. Move closer. At perhaps 500 kilometers, the field becomes strong enough to warp electron orbitals, the quantum mechanical patterns that define chemistry itself. The bonds holding molecules together, the bonds that make proteins fold correctly and DNA maintain its shape, start distorting. Proteins unfold, enzymes stop working. You'd die of physics before biology had time to fail. Not radiation damage, not heat, direct interference with the rules that make molecules possible. Closer still, under 200 kilometers, atoms themselves stretch into cigar shapes along field lines. Electrons can no longer orbit nuclei in their normal spherical clouds. Chemistry, as a concept, stops applying to you. What arrives at the magnetar's surface would be ionized gas, plasma that used to be a person, now just protons and electrons streaming along invisible magnetic rails. But here's where magnetars become truly terrifying. The 1979 event wasn't even close to their most dangerous trick. On December 27, 2004, a magnetar designated SGR 180622 suffered what researchers now call a starquake. The neutron star's crust, a solid layer of nuclear material under unimaginable strain, cracked. The magnetic field, anchored to that crust, whipped violently. In roughly 0.2 of a second, the flare released more energy than the Sun produces in 100,000 years. The gamma rays traveled 50,000 light-years and reached Earth. They measurably compressed Earth's ionosphere. The flare affected our planet's upper atmosphere from across the galaxy. Run the numbers on what would happen closer. Within a fraction of a light-year, models suggest that flare would have caused serious atmospheric damage, stripping ozone and allowing harmful ultraviolet radiation through. Even at several light-years, measurable effects remain possible, though far less severe. The implications are sobering even at interstellar distances. There are estimated hundreds of millions of neutron stars in the Milky Way. Not all are magnetars, but some are. And the unsettling reality is that quiet magnetars, the ones that haven't flared in centuries, are essentially invisible until they erupt. The catalogue of known magnetars represents only those that happened to flare while humans were watching with the right instruments. But extreme magnetic fields aren't confined to exotic stellar corpses. The same physics operates much closer to home, in configurations that threaten human survival in entirely different ways. Earth itself is wrapped in invisible danger zones called the Van Allen belts. These are regions where Earth's magnetic field traps energetic charged particles, protons and electrons from the Sun and cosmic rays, creating donuts of radiation encircling the planet. Stand unprotected in the inner Van Allen belt, about 600 kilometers above the surface, and you'd absorb a lethal radiation dose within minutes. Not from heat, not from pressure. From individual protons punching through cell membranes, shattering DNA strands, causing damage faster than any biology can repair. The discovery came almost accidentally. In 1958, James Van Allen's Geiger counters aboard Explorer 1 went haywire in certain orbital regions. Engineers initially suspected instrument failure. Then Van Allen realized the counters hadn't broken. They were being overwhelmed. Radiation so intense the instruments couldn't keep up. The protective magnetic field that shields Earth's surface was simultaneously creating concentrated death zones overhead. This creates a survival paradox. Without Earth's magnetic field, cosmic radiation would sterilize the surface within geological timescales. With that field, concentrated pockets of radiation become far deadlier than open interplanetary space. The shield saves you only if you stay under it. Venture through it, and you need speed. The Apollo astronauts understood this viscerally. Between 1968 and 1972, 9 crews traversed the Van Allen belts on their way to the Moon. Mission planners calculated trajectories that minimized exposure time, roughly an hour through the most dangerous regions. The astronauts absorbed total mission radiation equivalent to roughly 10 to over 100 chest X-rays each. They survived. A longer transit, say a stuck spacecraft, would have been fatal within days. But magnetic dangers closer to home don't end with the Van Allen belt. Earth's protective field itself isn't constant. It fluctuates in strength, it wanders in position, and periodically, over geological scales, it reverses entirely. North becomes south, south becomes north. During these reversals, the field doesn't flip instantaneously. It weakens, becomes chaotic and multi-poled, and can take anywhere from centuries to millennia to re-stabilize. During that transition window, the magnetic shield drops. What happens to life when Earth's magnetic armor fails? The geological record offers unsettling hints. Magnetic reversals occur roughly every few 100,000 years on average, though the timing varies wildly. The last full reversal, called the Bruns-Mutayama transition, happened approximately 780,000 years ago, long before modern humans existed. Brief magnetic excursions, like the Lachamp event, roughly 41,000 years ago, occurred when Homo sapiens were already walking the Earth. Our ancestors survived that weakening, but survival hides complexity. During reversals and excursions, models suggest cosmic ray flux at Earth's surface could roughly double as the field weakens significantly. Not instantly lethal, but elevated radiation exposure across decades or centuries would increase cancer rates, elevate mutation loads in reproductive cells, stress species already under environmental pressure. Some researchers have proposed, though evidence remains debated, that certain extinction pulses correlate with periods of geomagnetic weakness. The killing mechanism would be slow, not flash death, but generations of accumulated genetic damage. And there's a region where the field is already anomalously weak. The South Atlantic anomaly stretches from Brazil to southern Africa, a zone where Earth's magnetic field dips to roughly one-third its normal strength. Satellites passing through report increased electronic glitches as radiation penetrates shielding. Astronauts aboard the International Space Station report more frequent phosphenes, light flashes in their vision caused not by photons but by cosmic rays piercing their eyes and directly triggering retinal neurons. The particles are passing through their brains. The South Atlantic anomaly may be an early warning sign that Earth is entering another reversal. Or it may be a normal fluctuation in the complex dynamo of the planet's molten iron core. The honest answer is, we don't know. Instrumental records span mere decades. The process spans millennia. We're watching a clock whose hour hand moves too slowly to observe directly. So there are at least 4 distinct ways magnetic fields in space threaten human existence, each operating on different timescales and through different mechanisms. A magnetar flare within a fraction of a light-year would deliver a flash of gamma radiation powerful enough to strip Earth's ozone and cause mass casualties from elevated ultraviolet exposure. Death would come from above, invisibly, faster than warning systems could respond. Timescale? Seconds. The Van Allen belts trap radiation intense enough to kill any astronaut who lingers in the wrong orbital altitude. Space itself becomes poisonous in zones defined purely by invisible magnetic geometry. Timescale? Hours to days. A geomagnetic reversal would expose Earth's surface to elevated cosmic radiation for centuries or longer, slowly increasing cancer rates and mutation loads across all surface life. Timescale: generations. The South Atlantic anomaly already creates a region of measurably elevated radiation risk right now, affecting satellites, astronauts, and high-altitude flights passing through it. Timescale: ongoing. The physics underlying all of them reduces to one principle: charged particles follow magnetic field lines. When fields are strong and properly configured, particles get steered away from vulnerable surfaces, shielded. When fields are too strong, the forces tear matter apart at the atomic level. When fields concentrate particles, death zones form. When fields weaken, particles stream through unimpeded. Your survival at this moment depends on magnetic geometry you cannot see. Earth's field deflects the vast majority of cosmic radiation away from the surface. The Van Allen belts trap what remains at safe altitude. The atmosphere absorbs most of what penetrates further. Layer upon layer of invisible protection, all downstream from the churning iron convection cells deep below your feet. There's an open research question threading through all of this. could past mass extinctions be linked to cosmic magnetic events? The Ordovician extinction, roughly 445 million years ago, eliminated nearly 85% of marine species. Some researchers have speculated, though proof remains elusive, that a nearby gamma-ray burst, possibly from a magnetar or massive stellar collapse, could explain the pattern. The evidence would be subtle: elevated isotopes in sedimentary layers, damage patterns consistent with ozone loss, timing correlations with known magnetic field weakness. Future paleomagnetic studies may resolve this. Improved surveys of neutron stars and magnetars continue identifying how many lurk within dangerous range. Magnetometers distributed throughout the solar system could map the heliosphere's protective boundary in real time, providing warning of incoming particle storms. The invisible forces threading through space, forces that hold atoms together and guide charged particles along curved paths, determine whether any region of the cosmos is livable or lethal. You exist in a pocket where magnetic geometry happens to favor your survival. A few thousand kilometers up, trapped radiation would cook you. A few light years toward the wrong stellar remnant, field gradients would atomize you. And somewhere in the galaxy, right now, a crust is cracking on an object no one has ever seen. The magnetic field passing through your body at this instant, generated by Earth's liquid iron core, is the sole reason cosmic rays aren't threading through your DNA with every heartbeat. That field has shielded your ancestors for billions of years. It will likely protect your descendants for billions more. But it fluctuates. It weakens, it reverses, and when it does, the invisible architecture of space that keeps you alive rearranges into something less hospitable. The universe is threaded with forces you cannot feel, operating on scales you cannot perceive, holding lethal potential you cannot escape by running. The only protection is geometry, being in the right place where the fields bend in your favor. Like if this was interesting, hit the subscribe for more and turn that notification bell on.